The idea that senolytic drugs, those that target and eliminate senescent, or zombie, cells, might be used to treat Alzheimer's disease and other neurodegenerative conditions is gaining scientific momentum. While much of the early work on senolytics focused on improving musculoskeletal health, cardiovascular aging, or metabolic resilience, researchers are now looking closely at the brain, where cellular senescence may play a critical and previously underappreciated role in cognitive decline. If senescent cells are indeed contributing to the toxic environment that accelerates dementia, then their targeted removal could represent a novel and potentially disease-modifying intervention, something that current Alzheimer's treatments still fail to deliver. For a long time, Alzheimer's disease has been defined primarily by its pathological hallmarks: amyloid beta plaques, tau tangles, and progressive neuron loss. However, recent research has broadened this view, suggesting that neuroinflammation is not a secondary feature of the disease, but a central driver of its progression. In this inflammatory context, senescent cells appear to be key instigators. Studies have shown that several types of brain cells, particularly astrocytes, microglia, and oligodendrocyte precursor cells, can enter a senescent state under stress, such as oxidative damage, viral infection, or exposure to misfolded proteins like amyloid beta. Once senescent, these cells don't simply go quiet. They actively secrete pro-inflammatory cytokines, chemokines, and proteases that degrade the surrounding environment, a behavior characteristic of the senescence-associated secretory phenotype, SASP. This SASP creates a toxic milieu in the brain. It can disrupt synaptic function, impair neurogenesis, weaken the blood-brain barrier, and even encourage nearby healthy cells to enter senescence themselves. In short, senescent glial cells act as amplifiers of neural dysfunction. Animal models of Alzheimer's have shown that removing these cells, using either genetic tools or pharmacological senolytics, can significantly reduce neuroinflammation, preserve neuronal circuits, and improve memory performance. In one landmark study, clearance of senescent astrocytes and microglia in a mouse model of tauopathy led to reduced tau pathology and improved cognitive behavior, even when senolytic treatment was started after disease onset. This suggests a crucial insight. Even if senolytics don't reverse all damage, they may still interrupt the ongoing deterioration of brain structure and function. Unlike traditional Alzheimer's drugs that aim to block amyloid aggregation or enhance neurotransmitter levels, senolytics may address a deeper layer of the disease's biology, the cellular toxicity that prevents the brain from healing or adapting. Importantly, this approach is not necessarily Alzheimer's-specific. Other neurodegenerative diseases such as Parkinson's, frontotemporal dementia, and even multiple sclerosis show evidence of glial cell senescence and chronic inflammation. If senescent cells are a shared feature across these conditions, then senolytics could serve as a broad-spectrum strategy for neurological aging. That said, translating senolytics to the brain is not without challenges. Many current senolytic drugs, like dasatinib, navitoclax, or Physidin, have limited ability to cross the blood-brain barrier in therapeutically effective concentrations. Researchers are now developing next-generation compounds that are brain-penetrant or are exploring localized delivery methods, such as intranasal administration or nanoparticle-based transport. Another concern is safety. The brain is exquisitely sensitive to inflammation and cellular turnover. Indiscriminate clearance of senescent cells could cause unintended harm if essential support cells like astrocytes are lost too rapidly. This has led to interest in xenomorphics, a related class of drugs that suppress the SASP without killing the cells, offering a gentler way to modulate their harmful behavior. Human trials are still in early stages. Some pilot studies have explored the use of quercetin and Physidin, both natural flavonoids with senolytic properties, in older adults for improving physical function and reducing systemic inflammation. Whether these effects translate to meaningful improvements in cognition remains to be seen. However, the fact that several major research institutions and biotech companies are now actively pursuing senolytic strategies for neurodegenerative disease indicates growing confidence in the approach. What makes this field so compelling is its foundational premise, that aging itself is a modifiable risk factor, and that the same cellular processes driving joint degeneration and vascular dysfunction are also eroding the brain's architecture. If we can safely remove the dysfunctional cells that drive chronic neuroinflammation, we may not only slow the progression of dementia, we might delay its onset entirely. The vision here is bold but increasingly plausible, a future where early detection of brain senescence could lead to intermittent, targeted treatments that preserve cognitive health for years, even decades. While many hurdles remain, the possibility of using senolytics to protect and regenerate the aging brain represents one of the most exciting frontiers in both neuroscience and longevity science. And in a field where breakthroughs have been elusive, this cellular approach offers something rare, not just a new treatment, but a new theory of the disease itself.